Good morning, everyone. Thank you for logging on to our Take Action webinar series. Today is the 5th installment in the Take Action webinar series. This series is designed to bring you valuable information on the weed and herbicide resistance management topics, and it's a collaborative effort with the Take Action program and several land-grant universities. So joining us today on the call will be Dr. Mark Laux and myself. Dr. Laux and I have taken turns hosting these programs. So Dr. Laux from Ohio State University hosted the first 3 programs, and he helps us tremendously with the technology and with generating questions as well. So good morning, Dr. Laux. How are you?
Good morning. Doing good. Thanks.
Also this morning, we have Dr. Bryan Young joining us as a speaker. Dr. Young will be our first speaker. So good morning, Bryan. How are you doing?
I'm doing fine, Bill. Good morning.
Okay, before we begin, I will provide a little more information on the Take Action program. Farmers' freedom to operate is threatened by the increase and spread of pesticide resistance. The consequences include short and long-term economic challenges, decreasing land values, the uncertainty of the regulatory pathway and access to crop protection tools, crop losses, and other challenges. Take Action is a farmer-focused education program designed to help farmers and their advisors manage herbicide, fungicide, and insecticide resistance. The goal is to encourage the adoption of management practices that impact the resistant pests and preserve current and future crop protection technology. Take Action is brought to you by the Soybean Checkoff. For more information on Take Action, visit www.iwilltakeaction.com. As a reminder, you may submit questions throughout the presentations by using the chat box. We will allocate time at the end of the presentations to answer these questions. Our first presenter today is Dr. Bryan Young. Bryan Young is a professor of weed science in the Department of Botany and Plant Pathology at Purdue University. Bryan earned his bachelor's degree in crop and soil science at Michigan State and a Ph.D. in crop science with a specialization in weed science at the University of Illinois. Bryan has held academic appointments with teaching, research, and outreach activities for over 20 years. Bryan's research and education focuses on herbicide application technology and characterizing herbicide resistance in weeds. So our next speaker is Bryan. Bryan, I will turn the floor over to you.
All right, well, thank you, Bill, and welcome everybody this morning to hear a little bit of information I have on managing herbicide drift, and more specifically getting into discussion about what we call these days as drift reduction agents, formerly known, as drift retardants, drift control agents, a lot of different names, but because of the Extend technology, the popular term is DRA at this point. We're going to be talking about them for drift management, how effective they are at reducing physical drift, the weed control aspects related to drift reduction agents, and then also how it relates to any potential volatility with some of these dicamba applications. So broadly speaking, drift reduction technologies, that's anything that we can do to help mitigate drift, and a lot of that has to do with the management of those driftable fines. And so part of it has been through the use of drift reduction nozzles, low drift nozzles, such as we hear a lot about air inducted nozzles or Venturi nozzles, Turbo T nozzles. Those are just some of the types. And really, we've been managing drift of pesticides ever since we started using pesticides. But for herbicides, a lot of the focus have been on when we started moving into herbicide resistant crops, and more specifically, the Roundup Ready crops, because there we had a non-selective herbicide that we're applying in different use patterns, different times of year, and we had sensitive plants all over the place because everything was sensitive to it. And so that's when we started looking at drift management a little bit more. Plus, glyphosate or Roundup was and is a systemic herbicide, so it could tolerate having a little bit larger sized droplets and still maintain good weed control activity. And so again, a lot of this effort for drift reduction technologies came about mid-1990s. We had some before, but greater focus certainly since then. And in terms of management, we have physical or mechanical means of managing drift, and we have some chemical ones. Chemical would be where we talk about the drift reduction agents. But mechanically is where it started, and that's use of nozzles. And so you can see from these different nozzle types that are being marketed, different size droplets that are being emitted, all the way from fine, medium, up to extremely coarse and ultra coarse. So this has been one of the primary tools, and it should be the primary tool that we manage drift. I've had one mentor of mine that said for drift management, first start doing that mechanically and then address it chemically after that. So good drift management starts with the nozzles. And again, just showing different nozzles that are used for drift management, such as the Turbo T inducted nozzle, which has become popular with the advent of extend cropping systems. If you look at some of the marketing guides that we have on the different nozzle types and the best use of some of those nozzles for contact or systemic or even soil applied herbicides, you can see that you can find a nozzle that can perform fairly well in all these areas. But I would suggest that, take some of this with a grain of salt, because for systemic activity and having excellent efficacy using an air inducted turbo twin or some of these other nozzles, I think it leads us to question whether actually it will make for a good application or not. Depends on what size droplets you're actually emitting from those nozzles when you put them in your sprayer at your pressures and carrier volumes. So this chart is showing the American Society of Ag Biological Engineers, and this is the droplet size categories that they've come up with, the different micron sizes that I'm sure many of you are familiar with, going from extremely fine all the way to ultra coarse. So droplets less than 150 microns, which we would consider to be driftable, all the way to droplets beyond 600 microns, which are getting to be extremely large. So we have these different nozzles capable of spraying these droplet spectra that have this range. And pay attention to this column right here, retention on difficult to wet species. The larger the droplet, the more difficult it is to retain that large droplet on that surface. And especially if you have dew formation. Once you have dew formation on your target weed surfaces, that makes it even more difficult for those larger droplets to be retained and stick on that leaf surface. The other column I want to point your attention to is, what are these different size droplets used for? And if you go to these two larger sizes, the ag engineer suggests that extremely coarse and ultra coarse droplets are best used for liquid fertilizer applications. Systemic herbicides, we go back to the coarse size droplets. So droplets in that 350 to 400 microns in size. Looking at more nozzle information, this happens to be from Wilger. Again, focusing on the extremely coarse and ultra coarse droplets, moving over to what they suggest. Well, that's soil applied herbicides, which frankly, for a soil applied herbicide application, you just need to hit the soil. And that's really the target, the soil. And then after that, rainfall gets it in solution and moves it in the soil to where it can have an effect. Other than that, it's fertilizer applications for those really large droplet sizes, extremely coarse and ultra coarse. Even further, Greenleaf Technologies and some of their nozzles, they're saying, well, you can use some extremely coarse nozzles, but if you're using a systemic herbicide, it better be at higher carrier volumes. And that is certainly something that we've seen in the Extend crop management system. The first year out, 2017, we heard about 15 gallons per acre, but then after that, the focus has been, encouraging you to go to higher carrier volumes, make sure you get better coverage, such as 20 gallons per acre. So when it comes down to these ultra coarse droplets that we're using today, by label requirements for dicamba applications, some would recommend that they're good for soil applied herbicides or maybe fertilizers, but originally they were not designed for using with systemic herbicides like we are today. But why are we using them? It's for drift management. That is the main concern. That's why we have this requirement on dicamba labels for drift management. So some data out of University of Nebraska. Nebraska has been a university heavily involved with characterizing droplet sizes for use of different herbicide tank mixtures or adjuvant tank mixtures that might occur in extend cropping systems. and they look at the different droplet spectra that's being emitted from that final spray solution. And so here's just an example chart. But one thing I want to focus on is the Turbo T inducted nozzle, 11004. So that's that red nozzle with a dicamba product put in there. That is the reference nozzle that all spray droplet patterns, spray solutions and droplet patterns have to provide droplet sizes that are larger than that, or probably more accurate, I need to say, that you cannot have any more driftable fines than what this nozzle produces. And in just some laboratory testing, that nozzle with dicamba as the only component in the spray solution, it's running about 0.75% to 1% driftable fines, droplets less than 150 microns in size. So that's what we can get with just the nozzle itself, is getting driftable fines down to about 1% roughly, maybe 0.75%. Now, the use of drift reduction agents, that's been another thing that has really increased since the use of Roundup Ready spraying systems and crops. From 2010, I've been involved with publishing what's called the Compendium of Herbicide Adjuvants. And originally there were very few products in there, but 2016 edition, which is the last one that we've had, there's 155 different products for managing deposition, drift control agents, drift retardants, drift reduction agents that are now in that compendium. So there's a huge market for managing drift chemically in the tank that go along with the mechanical nozzles that we're using to help manage drift as well. So what are these products, these drift reduction agents? Well, there's in the Extend world, those that are approved for the dicamba formulations using in Extend crops is focused really on 3 broad chemistries, and that's polyvinyl polymers, polyacrylamides, and hydroxypropyl guar, which comes from the crop seed guar. So essentially it's guar starch. Now, all 3 of these have one thing in common. They increase viscosity of the spray solution. So I want to give you an example. If you think of disposable diapers, and once liquid hits those, they form into a gel. That's what these are essentially doing to spray solutions. Now, you don't want to get all the way to a gel, but certainly it will reduce the fluid characteristics, so it increases viscosity of the spray solution, and that results in fewer fine droplets and overall larger droplets. The challenge we have is when you have nozzles that create large droplets, and then you add on top of that a drift reduction agent, you have even larger spray droplets, which makes coverage a bigger challenge. So all the DRAs used right now in extended cropping systems will increase your spray viscosity. So it thickens your spray solution. So if we go back to our example of some of the data generated by Nebraska, if the benchmark nozzle, the Turbo T inducted 11004, will create, fines of 1% or maybe 0.75%, adding a DRA to that nozzle, you might get down to 0.5%. But in talking with Greg Kruger at University of Nebraska, he has told me previously that he's never seen any DRA plus a low drift nozzle get below 0.5 or 0.5% driftable fines. So we're not eliminating driftable fines, we're just removing a lot of that as a spray volume. So we're trying to minimize as much as possible, but nothing has been able to eliminate driftable fines altogether. So some research that I've been involved with, we looked at 4 different nozzle types. Venturi would be where that air inducted type nozzle comes in. And then we had no drift reduction agent, and then 2 different types of drift reduction agents. And we're looking at water sensitive spray cards here, and you can see that spray coverage is being heavily influenced by which nozzle you use, as well as the inclusion of a drift reduction agent. And so this for a spray pattern on a target weed surface may result in okay weed management, or it might have some challenges associated with it. I was at Southern Illinois University in my previous career, I guess you could say, my early part of my career, and there we generated data on some of these issues. And this is looking at spray coverage with glyphosate in the spray solution on common water hemp. And you can see that as we move from a standard flat fan nozzle to the Venturi or air inducted nozzle, we reduced spray coverage on that target by at least 10%. When we added a drift reduction agent, even at half X rate or 1X rate, we also reduced spray coverage, not to the same extent as the nozzles, but we still reduced them by up to 7% or so. So it compromised spray coverage even more so. And there was a correlation between that level of spray coverage and water hemp control. So the lower spray coverage you achieved, weed management with glyphosate, so water hemp control with glyphosate was also reduced. And that was not on glyphosate resistant water hemp, that was still on water hemp that was sensitive to glyphosate. This is a little bit busy of a figure, but the main thing I want to point out here is we had 4 different nozzles indicated by the different colors, and then we had the inclusion of different adjuvant systems, typically these drift reduction agents, as indicated by the different symbols you see within each color. On the x-axis, you can see spray coverage at the top of the canopy, and then what we're measuring here is water hemp control on the y-axis. So to get to the best spot, you want to have weed control that's at the top here. And what you see is you see some of these symbols with, I guess, a cross with a line through it. And that'd be an indication of treatments that did not include a drift control agent or a drift reduction agent. So we're able to get good coverage with those and good weed management. Where things fell apart, if you go down to the bottom here, you see blue coloration. That's an air inducted nozzle with a drift reduction agent included. So again, it kind of coincides with the previous graph where coverage relates to good weed control, even when you're using systemic herbicides. Here's some data out of the University of Missouri, Kevin Bradley's group, and he looked at 3 different nozzle types that can be considered low drift nozzles in terms of their design. And we have 2 different spray solutions, XtendiMax, which is just dicamba by itself, and XtendiMax plus Roundup Power Max. And then there were 5 different drift reduction agents included in each of those. And so what I want to bring your attention to is just that blue line is the reference for XtendiMax by itself within each nozzle type, and look at some of the orange bars that are less than that level of activity. So indeed, when spraying XtendiMax by itself using a drift reduction agent, there was some opportunity to see some reductions in water hemp control. Now when you add Roundup to that mix, using the red bar, you can see that there were fewer instances where we actually did reduce activity with the drift reduction agent. That's because in both cases, the Roundup, glyphosate, as well as dicamba are both working on that. And that's even in the case with glyphosate resistant weed species. Roundup or glyphosate still is contributing some level of weed control. Not a lot, certainly, but there's some value in that and helping improve the consistency of control when we're compromising spray coverage, more so than just dicamba by itself. So to summarize some of this work on efficacy of dicamba and drift reduction agents, large droplet sizes from ultra-low drift nozzles, I would suggest are marginal for getting consistent spray coverage and herbicide efficacy, even with some of our better herbicides, such as glyphosate, on weeds that are not glyphosate resistant. All the DRAs that we use within the Extend system, they're intended or designed to alter the spray viscosity, make it thicker. And so we know we are compromising spray coverage because we have more large droplets in that droplet spectra as we're trying to reduce some of the driftable fines. So when we combine these low drift nozzles and the DRAs, we know we're getting inconsistent spray coverage. That's why targeting smaller weeds makes sense, because once you have a jungle of weeds, it's even more difficult to get good spray coverage or on larger weeds. And we are seeing the potential for reductions in weed control. But be frank, these DRAs with the Extend or dicamba applications are required to manage drift, and that is required on the label to do so. So we are compromising the efficacy of some of these herbicides because of our current efforts to manage spray drift. Now, the other part of the topic I was going to discuss today is what does the use of these drift reduction agents, what do they contribute to potential volatility? Well, if I had my ideal situation after dicamba application, I would have all the dicamba that's been sprayed go into an Extend soybean plant because they can rapidly metabolize dicamba to a non-toxic form. So it can't do any damage. And it's not going to volatilize off if it's being metabolized by the plant or if it's inside the plant. So ideally, we'd get as much dicamba in these soybeans as possible after one of these applications. But we know that some of the DRAs can compromise spray coverage, and it might influence uptake of the herbicide in the plant as well. So that's where the basis is for whether these DRAs might influence dicamba volatility, because the more dicamba that remains on the leaf and isn't absorbed means there's a greater amount that potentially could volatilize off from that leaf surface. So what we did is we did what some would call humidome experiments, or we call ours vapor chamber. Essentially, it's just using a box, in this case, a plastic tub, to look at treated plants and how much dicamba vapor is given off from those plants following application. We use Clarity formulation dicamba as kind of a benchmark, an older formulation, and then the improved formulations of XtendiMax and Ingenia, which are labeled for use in Xtend crops. And we did use the full labeled rates of these herbicides in our spray application. In combination, we used 3 different drift reduction agents that represent the chemistries that are currently labeled for use in Xtend systems. So again, the hydroxypropyl guar type product, a polyvinyl polymer, and then a polyacrylamide that also contained a small amount of a surfactant in there as well. So we sprayed 6 soybean plants, as you can see in the picture, and then we put them in the tub. And those plants were treated at the V2 growth stage, so second trifoliate. They were placed in these chambers after application and taken to another remote location inside of a large walk-in growth chamber for 48 hours at conditions that would promote dicamba volatility. So that was higher temperatures, 35 degrees Celsius, 40% relative humidity, so pretty warm, low humidity. That's the conditions that we have observed increases the chance of volatility. And then we had air exchanges. So we exchanged the air and we're sampling that air through a filter to check for any dicamba that's being caught by that filter. So the air comes into the chamber, flows over the treated soybeans, and it goes out through the sampler through this filter or plug that we would call it, that we use for analysis of dicamba at a later point. So quickly getting to the results. You can see the 3 formulations, and we're not going to compare between the formulations today. Our research was designed to really focus on the effect of the DRAs, as you see listed here, within each formulation. So for example, Clarity, with no additional adjuvant applied, we had 4,590 nanograms per meter cubed. That's just a unit to measure how much dicamba we found in our air samplers. The most important aspect, though, is you can see that from that Clarity application, no DRA, when we included the DRA, we saw absolutely no change in the amount of dicamba in the air, so no change in dicamba volatility. And if anything, numerically, there's numerical reduction, but statistically no difference, but if anything, numerical reduction in the amount of dicamba found in the air that we sampled. If we move over to XtendiMax, same trend was true, that compared to having no DRA in that spray solution with XtendiMax, the DRAs did not by any means increase volatility. And then moving to the last formulation, Ingenia, we saw no increase in volatility. And if you want to, look at any difference, well, we actually saw a slight reduction in volatility when you use a polyacrylamide plus APG, which is that alkyl polyglucoside surfactant. And so our theory there is, well, maybe that additional surfactant allowed for more uptake into the Xtend soybeans, so it took it off the leaf surface where dicamba could volatilize from. So that's a potential theory. But the one thing I want to focus on is we did not see an increase in volatility with any of these DRAs, and that's the key point. So conclusions from the volatility aspect. We saw no evidence that these DRAs are contributing to commercial dicamba volatility, which is a good take-home message, obviously. But want to emphasize that we did we use 3 different DRA products, and there's a lot more that are currently approved for use in the Extend system. So these results are specific to these. We feel that they do represent a broad scale or broad number of these DRAs, but again, we didn't test all the formulations that are available commercially. So the worst case scenario would be increasing the amount of dicamba sprayed on the foliage, increasing rates of dicamba and not optimizing dicamba uptake into the plant. That'd be the worst case scenario. So from an application standpoint, I want to use the rate that's needed to give me weed control, make sure I'm using that or applying that in a manner that optimizes weed management. So dicamba remain on leaf surface, it's prone to volatility. I want to do whatever I can to get more dicamba into target weeds, but also soybean. So from a management standpoint, there's no widely accepted evidence that using one or more DRAs or more than one DRA is going to reduce off-target movement more so than just using one DRA. And we've heard of that practice. I used a primary DRA, but I use another one just because if a little bit's good, a whole lot more is better. We don't necessarily see that in some of our research that we've conducted. There is the potential that you're reducing spray coverage, which might compromise weed control, and that's where we get really concerned, is that if weed control starts dropping off and we still have physical spray drift, that is a definite problem. Another thing that we advise is make sure you're paying attention to your spray pressure, because as you start to slow your travel speed down, you might reduce your spray pressure with your rate controller, and that's going to compromise coverage a little bit more so. The opposite of that is if you increase travel speed too much, you're going to increase spray pressure, and that might increase driftable fines. A lot of people have gone towards larger spray volumes to increase spray coverage, which is good for weed management. But as we move to these ultra coarse droplet sizes for dicamba applications, the one thing I'll emphasize there is that these have never and will never optimize herbicide efficacy. It is just not designed that way. It's just something that we're doing to manage drift because we need to in this dicamba spray system. At the same time, it might be compromising weed control while managing drift. We just have to live with that potential sacrifice. So with that, I just wanted to say thank you for your time. I know that we're going to be addressing questions at some point. I'm not sure, Bill, if you want to do that now at the end of my presentation or save it towards the end of your presentation as well.
Okay, thanks, Brian. Lots of good information there. I think what we'll do is let's go ahead and hold the questions till the end. That's kind of what we've done in the previous 4 webinars. And so I'll get through my information, and we do have a couple of questions here that have popped up, so we'll want to hang on for those. These look like good questions. So we'll go ahead and get started. The next presenter is myself, Bill Johnson. I'm a professor of weed science in the Department of Botany and Plant Pathology at Purdue, so Brian and I work together. I have extension responsibilities. I have weed science extension and research responsibilities for agronomic crops, and I teach an advanced weed biology class in our senior seminar. So my experience is with the biology and management of herbicide-resistant weeds, weed control with cover crops, and interactions between weeds and other plant pests. So what I'm going to do today is I'm going to talk about some tank mix issues that we need to keep in mind for 2020. As our weed control systems are becoming more complex with the rapid spread and development and spread of herbicide-resistant weeds, we're adding more and more herbicides to our spray tanks. We also have the desire as well to add fertilizers and fungicides and insecticides to our spray tanks. And we're not going to hit on all of those issues today, but certainly our spray mixtures have become more complicated with time as our weed control challenges are increasing. So why do we utilize mixtures? Excuse me. Well, here's a list here, and I'm not going to read these off to you, but it's basically to increase the efficiency of our operations, to reduce the number of trips across the field. Sometimes we do this to get better activity on a specific weed as well. And again, as we move into this era where herbicide-resistant weeds have become driver weeds in many of our weed control programs, this is not going to go away anytime in the near future. Now, why are herbicide mixtures avoided? Well, incompatibility reasons, whether they do not mix well in the tank. You know, it could be a situation where it creates a precipitate in the tank that won't flow through the nozzles very well. You do have situations where antagonism occurs, and because of some physiological reasons, you have less activity on your desired target. One of the things that we'll address in the questions at the end, and this one will be specifically for Bryan, is that when we mix different types of herbicides, when we mix contact and systemic herbicides, we have different requirements on droplet sizes to optimize efficacy. So that's another reason why we might want to apply some of these products separately. Sometimes we see synergism and we see excessive crop injury. And one specific example I can remember, there's actually a couple of them, but back in the days when we used a lot of 2,4-DB to help with cocklebur, if we put that in the tank with Scepter, we would get more crop injury than if we applied those herbicides separately. More recently, if we put some insecticides, organophosphate insecticides in with herbicides like some of our ALS inhibitors and some of our HBBD inhibitors, we can see increased crop injury as well. And then the third reason is sometimes the cost is not justified compared to a single herbicide, and we used to think about that with grass herbicides and glyphosate. Now with some Roundup Ready volunteer corn becoming a problem, and certainly some of the grass issues that they're having in the southern U.S., there is a reason to add that grass herbicide to glyphosate. So where can herbicide antagonism occur? It occurs when a herbicide is mixed with something else and you get less control of the species that you're going after had you applied that herbicide alone. And this interaction can occur in the tank, it can occur on the plant leaf surface, or it can occur in the plant. And so I think this is an area of study that used to have quite a bit of activity back in the late 80s and early 90s. It kind of went away for a while. And now I think there's going to be more and more of us getting into this area, because in our efforts to solve problems for growers, we're going to have to be able to give better advice on certain things to do and to not do when these spray rigs move across the field. All right, so I want to discuss a couple of classic examples, and then I also have some more information that I want to discuss as well, related to mixing of a foliar fertilizer with herbicides, and some issues that have kind of cropped up in some of our fields here in the Eastern Corn Belt. So the first thing I want to talk about, again, here's let's see, let's get my slides in order here. I want to talk about the situation with, let's get to the right slide. All right, so this is the slide I want to be on right here. So before we had rapid adoption of Roundup Ready crops, in soybeans, we would tank mix things like our post-grass herbicides with broadleaf herbicides, and occasionally we would see lower grass control. So a classic example here was when we mixed herbicides like Sethoxidem, which is commonly known as Post or Post Plus. If that was mixed with an ALS inhibitor like Imazaquin or Scepter or Chlorimiron or Classic, typically we would get lower grass control, and specifically things like foxtail, barnyard grass, fall panicum were problematic ones that were very prevalent. As the Roundup Ready technology came onto the market and we started controlling grasses and broadleaves with glyphosate, this issue kind of went away, but nonetheless, that was a fairly big issue. More recently, in the southern U.S., glyphosate and clethodim in extend crops can be antagonized by dicamba, and this has resulted in lower grass control, and specifically some of the barnyard grass or jungle rice type species have become more problematic in these extend crops in Tennessee. So those are kind of some classic examples that we've dealt with in the distant past, and more recently, just last year in the state of Tennessee. Some of the things that we've faced here routinely over time, and this was fairly specific to a situation that occurred in the spring of 2018, is we know glyphosate or Roundup can be antagonized by atrazine premixes. And typically in our no-till corn production systems, which again are very prevalent here in the Eastern Corn Belt, this happens fairly frequently when we have cool conditions, and these cool conditions persist right up until the spray applications were made. And so these are cereal rye plots here that we're trying to terminate with Roundup and Roundup plus an atrazine premix mixture. And we can definitely see that at 2 weeks after treatment, we're getting much slower activity of the Roundup from being able to terminate that cereal rye. So we had this happen at a couple of locations, and we also saw this in a number of producer fields as well in the spring of 2018. And again, it was cool weather conditions that led up to this application, and this is the resulting activity that we saw with the glyphosate. And then again, I think some of the things that we're faced with recently, you know, much of the volunteer corn issues that we have here in the Eastern Corn Belt carries both the Roundup Ready and the Liberty trait. And so we are adding things like clethodim to our post-emergent soybean mixtures to try to pick up volunteer corn. But as we move into these soybean trait systems where we're able to use things like 2,4-D or like dicamba, the potential exists that we're going to see some antagonism of volunteer corn control. And what this series of pictures show you here is volunteer corn control. In the upper left-hand corner, this is a select product by itself. In the upper right-hand corner is select plus 2,4-D, and again, you can see that the volunteer corn control is less than what we would get with select alone. And then when we're in the lower right-hand corner, again, you can see the antagonism that 2,4-D is causing with clethodim on our ability to control volunteer corn. So again, some fairly significant issues that were being faced here. And again, these things are not beyond the realm of possibility on widespread acreages and are being incorporated in many research programs in the Midwest. Okay, so historically, what have been the solutions to these antagonism issues? Well, the most common thing to do is you increase the rate of your grass herbicide anywhere from a third to 50%, from 33% to 50%. Most of these herbicide labels will have statements on there that if you expect to see any antagonism, this is one of the recommended strategies. So the labels allow you to do this. The other thing that we do is if you go back again to some of these historical statements that were on herbicide labels, is you apply the grass herbicide first, you wait 3 days, and then you spray the broadleaf herbicide. Conversely, you could spray the broadleaf herbicide first, and many of these labels would state wait 5 days or more to spray the grass herbicide because it was the grass herbicide that was being antagonized. The other thing that these labels will say, and again, this kind of goes back to these post-emerge grass herbicides, use more of an oil-based adjuvant when you're using these group 1 graminicide herbicides, and then also because these graminicides are weak acid herbicides, make sure that you're adding ammonium sulfate if you have hard water questions about your water source to help overcome any antagonism that the hard water may be causing as well. And then obviously, you know, another recommendation is spray when your weeds are actively growing. So we have to make sure our weather conditions are optimal for plant growth, and that's always going to make these post-emergence herbicides work better than they do under cool conditions or drought conditions. All right, so that leads me into this topic that I want to spend a little bit more time and go into a little bit more depth on. So a little over a year ago, we started getting a number of questions into our office about utilizing a sulfur source, a liquid sulfur fertilizer source as a tank mix partner for burn down applications. And the historical perspective on this is because of the Clean Air Act, we no longer have nearly as much sulfur deposited into the atmosphere and onto our fields in the Eastern Corn Belt. We do now have some soils that are sulfur deficient, and our crops are responding to sulfur fertility. So the reaction to that then is we find sulfur fertilizer sources that are economical to use and can provide that boost in yield. And so one of the sources that was cheap and is desirable to use by custom applicators is a product called ammonium thiosulfate. And ammonium sulfate is shown here. And again, the second bullet point kind of shows you some of the yield response that has been seen, up to 22 bushels per acre. And again, this is on a sulfur deficient soil, 22 bushels per acre for corn and 13 bushels per acre for soybean. And the rates, in order to give us 20 pounds of sulfur, are somewhere in that 7-gallon region. So there's been a number of adjuvant studies conducted in the past where ATS was viewed or was evaluated as a potential substitute for AMS. But typically those rates as an AMS substitute were about 1.5 gallons per acre. So we just didn't have information on these higher application rates, the 7-gallon per acre application rates, and how that would impact the efficacy of our burn down herbicides. So we initiated some studies in the greenhouse last spring using some indicator weed species that respond very well in adjuvant trials. So the species that we evaluated were wheat, which is a good grass mimic, kind of a challenge to control with straight glyphosate, so it is fairly responsive to adjuvants. Velvetleaf and common lamb's quarters are good test species for glyphosate as well, because again, they can be kind of tough to kill, and it's relatively easy to tease out the adjuvant effect on something like this. So here's some examples of the results. So this first series of slides that I'm showing you here is wheat, and this is control 14 days after treatment. And what this shows you here is a non-treated pot of wheat on the left, and then the first one is glyphosate alone. The second one is glyphosate with AMS, and you can see that when we have hard water, we definitely get a quicker activity and more complete activity of glyphosate, and being able to turn to control the wheat. When we add a low rate of ATS, what you can see here is that this shows you that we did inhibit the activity of glyphosate in terminating this wheat. And then when we add the high rate, so this would be the 7-gallon rate of ATS, you can see again even more antagonism. These last two pots show you what would happen if we added ammonium sulfate back into the mix with the glyphosate and the ATS. And what this shows you is that the addition of ammonium sulfate does not overcome the activity of the antagonistic effects of ammonium thiosulfate. So what happens? So in the Eastern Corn Belt, we rarely apply glyphosate by itself unless we're trying to terminate a cover crop. And most of the glyphosate is going to go out with some kind of a broadleaf herbicide, because so many of our acres have mare's tail and other winter annual weeds, and also some summer annual weeds that we're attempting to terminate. So again, this is also 14 days after treatment. The pot on the left shows an untreated. The second pot is glyphosate plus 2,4-D. The third one is glyphosate 2,4-D with ammonium sulfate. And again, you can see here that 2,4-D was very capable of antagonizing the ability of glyphosate to control wheat, compared to the previous slide with glyphosate alone, where we were able to terminate it pretty effectively. When we look at the treatments where we added ATS, again, here's the low rate, here's the high rate. We can see the antagonism as well, and you can see we get even less control of this wheat when we have both ATS and 2,4-D in the tank versus what we get with straight glyphosate. So to look at this information in more of a graphical format, we'll take a look at this slide right here. So this is a bar chart that basically shows you all of the information that was shown on the previous two slides. So here's glyphosate alone with the low rate of ATS and with the high rate of ATS. When ammonium sulfate is added, you do improve the activity 5 to 10%. When 2,4-D is in the tank, we never do get complete termination of the wheat. And when we add ammonium sulfate back to it, we can improve the activity of glyphosate alone. But again, still not quite as high as what we're getting when we don't have 2,4-D in the tank. The other thing that we tried to do in these adjuvant studies is we're always trying to kind of figure out why the antagonism is occurring. And so we collected the spray solution pH of all these solutions. And what you can see here is as we go from glyphosate alone to adding a low rate and then a high rate of ATS, we're increasing the pH of our spray solution. So we know that these weak acid herbicides typically work better when the spray solution pH is low. So one of the reasons that we're getting this antagonism could be due to the fact that we're increasing the pH of the spray solution and possibly getting less of the herbicide into the plant. So one of the things that we need to do in the future is adjust the spray solution pH back down to these lower levels and see if that helps to overcome any of the antagonism. So again, that's not going to be the complete answer to the story, because we do see some relatively rapid burning of the plant tissue when we get the higher rates of ATS, but that may be a way to help us overcome some of the antagonism that we're seeing. So I'll just show you a few pictures here with ATS and glyphosate on Velvetleaf, and it's basically the same trend. We see here's glyphosate alone, glyphosate plus AMS. AMS definitely helps with Velvetleaf control. And then where we have the ATS in the tank, we definitely see the same type of antagonism that we saw with wheat control. The beauty with a broadleaf weed control is typically we're usually adding 2,4-D, dicamba, sharpen, metribuzin, or some other broadleaf herbicide to the mixture. So we don't worry quite as much about broadleaf weed control as we do grasses, and we're able to overcome that. But nonetheless, we still see some of that same effect, and that's kind of shown here on this graphic. Okay, so the conclusions from this is that we definitely proved that ATS and 2,4-D can reduce glyphosate efficacy on grasses. We saw that it can reduce the efficacy on broadleaf weeds. Again, we're not recommending to people to avoid sulfur fertilization. You just need to recognize that if you're controlling some of these tougher to control weeds, that you do need to make some adjustments in what you do to your spray solution in order to avoid having to make another trip over the field. So again, recommendations would be increase glyphosate rate, add ammonium sulfate to overcome any hard water issues. Again, this is a no-brainer here, adding in another effective mode of action for broadleaf weed control. We need to look at this more in our research program, but certainly if you have the ability to adjust the spray solution pH, make sure you get that back down to kind of the optimal place where glyphosate is going to work best. So here's some ideas for future research areas. Again, I'm not going to read these off, but again, a number of different areas that we could work on in the future, and I think some things to kind of think of as we kind of plan some of our larger spray applications for this spring. So I think with that, we're at the end of my presentation. So I think what I'd like to do at this time is go get Bryan back on the phone here or on the line, and we'll go ahead and ask a few questions. So Bryan, one question that popped up is, do most herbicide labels have recommendations on the proper droplet size to shoot for to maximize efficacy?
Yeah, that's a good question. So it's addressed by a lot of the herbicides, but I wouldn't say they're not on all herbicide labels. In some cases, they'll just describe droplet size pretty generically without saying, a certain micron size. They'll say use medium-sized droplets or use a coarse-sized droplet, but there's different categories of coarse. There's ultra coarse, extremely coarse, very coarse. And so they don't do a great job. Some do a lot better than others. So that is one place to look for in terms of what is the ideal droplet size. But then you also have to pay attention to that, the carrier volume that they recommend too, because it's not all about droplet size. Carrier volume, they're related in terms of achieving the necessary coverage.
Okay. And with that thought in mind, so I know out in the marketplace there's going to be some challenges with combining the glufosinate herbicides with some systemic herbicides and optimizing coverage. And how are we gonna make these systems work, and will it still keep us in compliance with some of the stewardship guidelines, say in the Enlist soybean system?
Well, it's going to be a challenge in some cases, because one thing I recommend for any herbicide mixtures is make sure that each herbicide in that tank, you're trying to optimize it for control of whatever weed you're throwing in the tank for. So if you're putting glufosinate or Liberty in the tank, and it's for water hemp control. Make sure you're applying Liberty in the best way possible to control that water hemp species, or maybe it's mare's tail. Now, if you have Liberty plus 2,4-D as one example, well, there are some areas where they overlap the 2,4-D choline. So like in list 1 and Liberty formulation on their label, that there's overlap in terms of the droplet spectra that they both recommend, and the nozzles and adjuvant systems and carrier volumes that they recommend. So there's opportunity for that. You can potentially optimize both herbicides in combination. And it's not, you can't do that for all herbicide applications though. And one that I'll just point out is dicamba is difficult in Extend systems because the extremely coarse and ultra coarse droplets that it recommends, and you can't use ammonium sulfate as an adjuvant system. Whereas a lot of other herbicides that we like to use today, we do like some of the smaller droplets, not those really big ones, and we do like the use of AMS.
Okay. Okay, I think that covers the main questions that we had. So this is going to wrap up today's presentation. A recording of this webinar will be available on the Take Action website within 1 week. And next week, we have 2 new speakers. We'll have another webinar with Dr. Kevin Bradley and Dr. Joe Eichley as speakers, and they will discuss the status of on-combine seed destruction, so seed terminators. And then Joe will talk about enlist mixing issues. So I think if there are no other questions that kind of pop into this chat here, I think we're done with this week's webinar. I want to thank everyone for joining in. And again, just a reminder that we will have a recording of this available. So if you have other folks within your organization that would like to listen to this, that it will be available. So thanks everyone, and we'll plan on talking to you next week.